This is what I took an hour to say last time. So let's recall the words at least. So okay, so what we're gonna talk about is a categorical action of the braid group. So there's a category, and the braid group acts by endofunctors of this category, invertible endofunctors of this category, autoequivalences of this category. What kind of category is it? Well, it's a category of modules over an algebra. Well, not quite. It's a category of complexes of modules over an algebra. But so what was the algebra? The algebra was the zigzag algebra, which is a quotient to the path algebra of this quiver by some relations. Or the relations, if you recall, were if you go twice in any direction, we declare that path to be 0. Twice to the right is a length 2 path, which is 0. Twice to the left is a length 2 path, is 0. So what length 2 paths do you have left? You've got the loops at any given vertex. Like here, there's a loop, a length 2 path like that. There's a length 2 path like that. We declared those to be the same. So those were our zigzag relations. So this is an algebra. It's a graded algebra. Graded the basis of paths here is graded by path length. Okay, now we have for each vertex little I, we've got a left module, which is as a vector space just the paths which end at I. Paths which end at I has a left action of the algebra. The paths which start at I has a right module, and we define these bimodules just by tensoring together a left module and a right module. These are some bimodules, and what I claimed and what we partially proved, and what I think I put on an exercise in the homework to finish, was that these bimodules and their tensor products categorify the temporally Lieb algebra, or a quotient of the temporally Lieb algebra. So if you take these bimodules and you tensor them together and you look how they decompose, that the decomposition you see is exactly the defining relations of the temporally Lieb algebra and its standard basis. And that's important because we're trying to define a braid group action, and the braid group action we're going to define is going to use these bimodules in an essential way. Okay, so what are we going to do? So where are we headed? So the most important thing today, the first thing we're going to, well, the second thing we're going to do is extend this to a braid group action. So I'll tell you a little bit about the braid group and then explain the definition of the braid group action. And then discuss so I haven't even told you precisely which category the braid group is acting on, but I'll choose on, let's say, so this is going to be the category of bounded complexes of the AN modules. So the braid group is going to act here. And the theorem, the important theorem here, which to some degree we will discuss for both in this talk and in Friday's talk, is this action of Bn plus 1 on category C is faithful. So this theorem is due originally to Kovanov and Seidel, and also in the case of the 3-strand braid group, independently due to Ruquier-Zimmermann. It's really quite fascinating. Kovanov and Ruquier have, at several points in their illustrious careers, independently thought about very similar things. This is not the only major theorem that they share independently. Those of you who know anything about categorified quantum groups will recognize both their names in the world of categorified quantum groups. I think this is a fundamental theorem. So how do you tell people that you think a theorem is fundamental? You prove it in lots of different ways. So I know 7 proofs of this. Although 2 only work for the 3-strand braid group. So I think what I'm going to try to do, and I mean, These are logically independent proofs, but they each shed a light on a different perspective on the braid group. So it's interesting to see which features of the braid group show up in which proofs. So the real goal for the part of this talk and all of Friday's talk will be to tell you as much as I can about all of these proofs. Okay. But before I do that, so I made the mistake of, in looking at the timetable, instead clicking on the original abstract I submitted months ago for these lectures. And the title was Geometric Representation Theory, and I don't think I've said any of the words that were on that abstract. So, so I kind of want to try to do that justice a little bit. So this action and this zigzag algebra are part of geometric representation theory, and they're also part of Kovanov homology. Hopefully we'll see a little bit. So for a few minutes, I want to, well, to tell you a story, which is the story of Kovanov's discovery of Kovanov homology. So as I've been informed many times, like the first time I applied for jobs, and by my wife many times, and things, I'm not a topologist. So, so what am I? So, but I am interested in knot homologies, and Kovanov, at least originally, was also not a topologist. And I think it's maybe interesting in the spirit of trying to say what role geometric representation theory has in this story to say a little bit about how Kovanov discovered Kovanov homology. So, unfortunately, well, fortunately and unfortunately, nowadays, and even originally, when people learn Kovanov homology, they don't read Kovanov's original paper. Usually people read Barnaton or something more accessible, which is great, except at a minimum you should read the introduction to Kovanov's paper. So let me tell you a little bit about what's in the introduction of Kovanov's paper. So this is maybe around 1999. So so Kovanov starts by talking about two classes. He says, in the first sentence of the introduction, he describes two classes of invariants that show up in low-dimensional topology. On the one hand, there's things like the Jones polynomial and Homfly polynomial, and maybe just a bit more broadly, quantum invariants. These are things, many of which, I mean, there are many definitions of some of these things, but they all have some perspective which comes from representation theory of quantum groups or semi-simple Lie algebras or something like that. I mean, maybe Witten, Reshetik, and Tarayev invariants of three manifolds would go here. So this is sort of one world. These invariants are all essentially combinatorially defined. And from the very beginning, it was clear that they were combinatorially defined and algorithmically computable. On the other hand, up here then we have maybe Floor or Seiberg-Witten, three manifold invariants, and then there's maybe Donaldson or Seiberg-Witten four manifold invariants, etc. So these, and now I'm speaking as of 1999, were not algorithmically computable, not combinatorially defined, and to compute them, one needs to use some interesting structures, you know, Seifert fiber rings or something like this in different cases. So Kovanov says, I mean, so at this stage, these two pictures barely know each other. So it's interesting to think about that now. Now, I mean, they haven't had a kind of consummated romantic relationship, but they certainly have a beautiful friendship at least. So, but Kovanov says something interesting, and it's interesting. This paper on the categorification of the Jones polynomial says nothing about the relationship between these two things. But nonetheless, in the first two sentences, this is what he talks about. So, but then he makes the observation. He says, but they are kind of connected. So, if you take the Euler characteristic of these guys which are not algorithmically computable, if you look at the Euler characteristic, then you start seeing things that are closely related to things here. And the example he gives is the example of the Casson invariant, which is the Euler characteristic of the Floor three manifold homology. And this Casson invariant is closely related to the Alexander polynomial, which is certainly something that deserves to be over here. So somehow at this stage, these things which are not algorithmically computable have Euler characteristics which are algorithmically computable. So, so he looks at this picture and then says, okay, so now we can ask a speculative question. What does this picture tell us? It says, well, what on earth is up here? So he chooses to pose the question of why he's doing what he's doing, which is going to define an object which lives up here, namely Kavanagh homology, whose Euler characteristic is something which lives down here. And the reason to ask this question is motivated by something happening over here. So that's why he asked this question. Now, so now you could ask, fine, once he asked this question, how is he going to answer it? In other words, if you want an object up here whose Euler characteristic is the Jones polynomial or something, where do you look? And this is where geometric representation theory comes in, because Kavanagh already knew where to look. So where to find a categorification of the Jones polynomial. So I want to spend a couple minutes on this, in part because I think some of the names and mathematics involved here are maybe not so well known to members of this audience, so it's good to see. So, well, how does a representation theorist think about the Jones polynomial? Sometimes, at least. So there's a world of representation theory, which is the representation theory of the quantum group UQSL2. Or you could think about other quantum groups if you wanted other invariants. So an example is this quantum group. This is in particular, this is an algebra. It has a two-dimensional representation, which I'm calling V1. And this is a Hopf algebra, so you can take tensor products of representations. And so an example of a representation is the nth tensor power of this guy. And the nth tensor power of the two-dimensional representation of SL2, of course, it has an action of UQSL2 on it, but it has a commuting action of the Temperley-Lieb algebra. So this is an appearance of the Temperley-Lieb algebra in representation theory. And so in particular, it's got the braid group acts here, commuting this UQSL2 action. So this is a kind of structure that's part of representation theory. And now there's some black box, which I'm not going to talk about at all, not now, but this is something that we could come back to later in the term. Now you do this, and you get link invariance. Invariance of links in the 3-sphere, like the Jones polynomial. So somehow the basic input for the Jones polynomial is this particular representation of UQSL2 equipped with its Temperley-Lieb action. Okay. So the reason, so Kavanagh, so it might be reasonable if you're trying to categorify the Jones polynomial, you could think about categorifying this structure, or you could at least ask, could we categorify this structure, the input for this this big black box? And this is what Kavanagh already knew how to do, because this structure had essentially already been categorified in earlier work kind of involving many people. So a kind of precursor, this is maybe a pre-question to the question of how can you categorify the Jones polynomial, is how can one categorify, say, V1 tensor n with its maybe UQSL2 action, or maybe with its braid group action, or Temperley-Lieb action. And here, so here the motivation is an extremely deep theorem about SL2 and about semi-simple Lie algebras. So why should we be able to lift this structure, to categorify this structure? Well, so let me just say something briefly about what kind of things you have here. So if you have a representation of UQSL2, then there are two very important vectors, the raising and lowering operators of UQSL2. So these are particular elements here which act on any representation. And so now here's a rather remarkable theorem. So this is Lustig and also independently Kashiwara. And this is maybe late 80s, late 1980s. So every finite dimensional representation of UQSL2 has a canonical basis with remarkable properties. So I'll say a piece of what remarkable properties means. In particular, say so if V is a representation of UQSL2, then there is a basis canonically defined, depends on no choice at all. Let's call it a V1 through Vk, such that if you look at the E and F, and you write them, so now we've chosen a basis of this vector space, so the action of E and F is given by some matrices. So the matrices of E and F have non-negative integer entries. Integral entries. So, I mean, we're working with Q's, so the entries are in N, Q inverse. So this is a remarkable fact, which, in particular, if you don't know what a quantum group is, but you know what SL2 is, SL2 is trace n by n trace 0 matrices, just forget about the Q. Set Q equal 1. What we're saying any representation of SL2 comes equipped with a basis with respect to which the generators of SL2 act by matrices with entries in the natural numbers. So the entire finite dimensional representation theory of SL2 can be formulated over the natural numbers. So this fact was, should have been discovered in some sense, 100 years before this, or could have been. So now comes Igor Frankl. So Igor Frankl asked, why does this hold? Why can the representation theory of SL2 be formulated over the natural numbers? These natural numbers should be dimensions of some vector spaces appearing in mathematics. What vector spaces? So which vector spaces have these dimensions? I mean, that's not a very well phrased way to say it. But that is why, so Frankl postulated that one should be able to categorize the structure in order to explain this positive integrality. And and in particular, I mean, so by the way, this theorem is not about UQSL2. This is about a quantum group associated to any finite dimensional semisimple Lie algebra. This statement is much larger than this, but used in this pace. So that is why, and so around the time he asked this question, Kovanov was his PhD student, and then there's a kind of remarkable theorem of Bernstein, Frankl, Kovanov, which answers this question in this case. In particular, they explain that this representation of UQSL2 in the temporally Lieb algebra is the Grothendieck group of a category appearing in infinite dimensional representation theory. This is category O for GLN. It's maybe a singular block. This is technical. This is a category of infinite dimensional representations of SL2 this category has growth in group equal to this tensor product representation. And the action of UQSL2 and the action of the temporally Lieb algebra can be lifted to endofunctors of this category, or the derived category. So those functors are called translation functors or Zuckerman functors, depending on which side you're on. So I don't expect that that means anything to anyone directly. The point I'm trying to make here is that the input for the Jones polynomial had been lifted categorically to this particular category with this extra structure on it. In particular, this temporally Lieb algebra had been categorified, acting here. And the categorification of the temporally Lieb algebra that we're studying is, in fact, a very small slice of this picture. It's just we've just picked out, in this zigzag algebra story, we've just picked out by generators and relations a very small piece of this. And so in particular, Bernstein, Frankel, Kovanov conjectured in their paper, and their papers sometime in the mid to late 1990s, they conjectured that you should be able to write down, essentially they conjectured that you should be able to use this to define a knot homology theory which categorifies the Jones polynomial. So the existence of such a thing was known to Kovanov, and their conjectures, so their conjectures about how to do this were all eventually became theorems. This is the proof of all these conjectures, and the construction of Kovanov homology using this is some remarkable work of Katerina Struffel. So Struffel carried out this piece of the BFK conjectures. So at this stage, I think this is maybe around 1997 or something like that, it was clear that there should be a knot homology which categorifies the Jones polynomial. And how complicated should it be? Well, pretty complicated. Certainly looks as complicated as Seiberg-Witten theory or something like this. It's just algebraic, not geometric. So a piece of Kovanov's brilliant insight, and that's maybe why it's Kovanov homology and not Bernstein-Frankel-Kovanov homology, is that Kovanov realized that in this particular case, once you know this thing exists, you should just be able to define it independently. You don't need to know what category O is to define it. But you do need to know what category O is in order to know that it should exist. And that is where geometric representation theory entered in the prehistory of the quantum invariant side of categorification. Okay, so thank you for indulging me in that, Liam. That's partially for you. But of course, this story is all close to my own mathematical genealogy, so it's kind of fun to get to say something about it. Okay, any questions before we go on to braid group? All right. Okay, so let me say a couple things about the braid group. Again, where we're going is we already have an action of the we already have a categorification of the temporally Lieb algebra. We want to extend it to a categorification of the braid group. So the braid group, Bn, there are several points of view on it, and all of them will be important. One is this one, which Ellie mentioned in her talk. This one will appear and play a prominent role on Friday. So this is Friday. Friday is topology day. So today is algebraic combinatorics. So for us today, the braid group is the generalized braid group of a Coxeter group. Which Coxeter group? The symmetric group, namely Sn. So the symmetric group, when you think of it as a Coxeter group, that means you're thinking of it in a particular presentation. So the symmetric group is, as a group, I have generators I equals 1 through n minus 1. And what are the relations? So you should think here Si is the transposition of adjacent letters, I and I plus 1. So what are the relations in these generators? Well, they all have order 2. And what are the other relations? Well, the Coxeter relations in this case say that if I and j are far apart, then the generators commute. And otherwise, the generator's braid. Plus minus 1. So this is the Coxeter presentation of the symmetric group. And if you for any Coxeter group you have, in particular for this one, there's an associated braid group, which is what you get by looking at the same presentation and just removing this order 2 relation. So you take sigma I and or the braid relation. So this is one of the important presentations of the braid group. And you can see from this construction, there's a surjective group homomorphism that just takes sigma I to Si. We just impose more relations here. And this group homomorphism has a section which is just a map of sets, whose image are what are called the positive permutation braids. So you take an element in the symmetric group, you write it with as few of these letters as possible, and then you just write the corresponding braid. So in this section, if you have the braid S1, S2, S3, S1, the associated positive permutation braid is sigma 1, sigma 2, sigma 3, sigma 1. Another way to think about this is if you draw a permutation just by crossing lines in the plane, then just think of all those crossings as positive crossings. Draw it in with as few crossings as possible. Think about them all as positive crossings. That gives you a braid. So inside here, there's let me write it over here. There's the image of this section. These are the positive permutation braids. Okay. Now, one other piece of structure that I want to look at is the monoid generated by these positive braids. So the positive braid monoid. So in particular, let's look at this presentation of the braid group up here. So sigma I and relations. And this, we were assuming, was a presentation of a group. So in particular, that means that all my generators, I formally added inverses and any relations about those inverses that are implied by associativity in these relations, and conjugation, etc. But you could also take this same picture and think of it as not presenting a group, but rather presenting a monoid. So let me call this Bn plus. So it's exactly the same picture, same relations, but I just think of it as presenting a monoid. So I don't formally throw in inverses here. So there's, of course, there's a canonical map from here to here, map of monoids. And a question you can ask is, what can you say about this map? So in particular, a natural question is this map injective? So is this map injective? This is not an easy question to answer. So this map is injective. This is a theorem of Deligne. Deligne, and also of Brieskorn Saito. This is in the early 1970s. Is that this map is injective. So the braid monoid embeds into the group. In order to prove this kind of statement, what you need to prove is that this monoid embeds into some group. Because if you can show that this monoid embeds into some group, well, any map from this monoid to a group factors through this group. So if you can show that this map is injective for some group G, then it follows that this map here has to be injective. Okay. So armed with the knowledge that this map is injective, we can think about the monoid generated by the positive crossings in a very combinatorial way, because we can just use these kind of relations. Okay. So maybe one other thing to say is the question of is this map an injection? One way to say it is, suppose you're in this group and you look at two elements, you look at two expressions for an element which can be written as a word in just the positive generators. So can you move between those expressions using only braid moves for positive generators without ever having to use an inverse? And the answer is yes, you can. So one consequence of the faithfulness of the braid group action that we're going to define is it gives a new proof of the injectivity of this map. So it gives a linear, so Deligne's original proof and Brechot-Saito's proof are not linear algebraic. So one consequence of the faithfulness is that it will give a linear algebraic proof of this theorem of Deligne and Brechot-Saito. So I'll explain that in due time. Okay. Okay, so let me just introduce a little bit of notation. So these positive permutation braids in here, I'm going to write as Sn tilde. These are the positive permutation braids inside here. Inside here. Okay, so now the categorical braid group action. So if you looked at the homework exercise, the homework exercise essentially told you what you need to know in order to define the braid group action. So recall that we have the bimodules UI. So this is a grading shift of the tensor product of a left module and a right module over the zigzag algebra. So let's consider, so I claim that there is a bimodule map from this, we'll call this M, a map of AN bimodules. So what is this bimodule? This is that consists of a linear combination of things of the form a path ending at I and a path starting at I. Okay, so that has an action of the path algebra on both sides, the zigzag algebra on both sides. On the other, so there's an obvious bimodule map. I mean, obvious if you think about what it means to be a bimodule map, staring us in the face here. So does anybody want to tell me what it is? So I have a path ending at I and a path starting at I, and I want to produce a path. Just concatenate them, right? So the multiplication in the algebra, that's a bimodule map. Okay? So in particular, I'm going to call this sigma I check. I want to think of this bimodule map as defining for me a two-term complex of bimodules. So I can think about this as a complex if I just put a 0, think of a 0 here and a 0 here. So this is a complex, a two-term complex of bimodules. Okay. Now, something which I put on the exercises but is less obvious than this. Oh, and by convention, by the way, this term AN is sitting in homological degree 0. Okay. So let me define sigma I. So there's actually a bimodule map the other way as well. So there's a bimodule map from AN to a shift of UI. This is less obvious. It's a kind of, the condition that this is a bimodule map is quite strong because to be a bimodule map, you have to intertwine the left and right actions of A. So in order to define a bimodule map, you just have to say where 1 goes, but 1 can't really just go anywhere at all, because if you act by the left, on the left by A, that tells you where A goes. So A has to go to A times f of 1. But on the other hand, it also has to go to f of 1 times A, because you could have gotten A by the right action or the left action here. So the image of 1 here is quite constrained. It has to be an element in here which satisfies this relation. And there's just not that many elements here that satisfy this relation. I think up to scalar, I mean, there's just up to scalar, there's just one such element, especially if I tell you the degree. So if you play around for a little bit, you can write down a 2-term complex of bimodules like this. And again, this, by convention, this AN is in homological degree 0. Okay, so there's a theorem. This is Ivanov-Seidel and also Ruquier-Zimmermann, which is they tell you what relations are satisfied by these complexes of bimodules when you start tensoring them together. So if you do so the first is, well, I'll write them down and then we'll talk about them. Okay, so if we start tensoring these complexes of bimodules together, you can tensor bimodules together, so you can tensor complexes of bimodules together and get new complexes. There's no derived tensor product here or anything else like that. This is much more, algebraically, this is much more basic than the kind of stuff, algebra that shows up in Adam's series, lecture series. So the first, so if you take the tensor product of sigma I and sigma I check, that's isomorphic to just the bimodule AN by itself. So isomorphic where? In the homotopy category of bimodules. So if you tensor these bimodules together, just naively, you don't just get a one-term complex of bimodules. You get a big complex of bimodules. But that complex of bimodules is homotopic to this complex of bimodules. So this is in the homotopy category of bounded complexes of AN bimodules. So this is, so there's a little bit of homological algebra here in this, which for the moment I'm not going to elaborate on too much. And if you start taking sigma i's for different indices, then in the homotopy category they braid. So if you look here, you see the braid relation. So let's think about this a little bit. And by the way, this is just a computation. This is, but it's a computation which is natural to consider when you think about, so recall the map from the braid group to the Temperley-Lieb algebra, which sent sigma I to 1 minus q ui. So we have just interpreted this linear combination as a two-term complex. So okay, so why am I referring to this as a braid group action? Well, so let C be the category of complexes of left AN modules. So an object here is and actually I only want to deal with projective modules. I just want to think about complexes which are built from our left modules pi that we know about. So is a complex whose chain groups are just direct sums of pi's, maybe with grading shifts. So this is a complex of an modules. Now, if I have a left an module and I have an an bimodule, I can tensor the two together and get a new an bimodule. So if I have a complex of an bimodules and I tensor it with if I have a complex of modules and I tensor it with a complex of bimodules, I get a new complex of modules. So this is important. The sigma I, these are complexes of bimodules. They define functors from, which I'll denote by little sigma I, from C to C. By taking a complex to the complex tensored over an with the complex of bimodules sigma I. So so these guys define endofunctors, and so you can think of these complexes of bimodules in two ways. You can think of them as complexes of bimodules, or you can think of them as endofunctors of the category C. And this latter way is what we mean when we say we have a braid group action. So rewritten in terms, so if you rewrite this theorem thinking about these things as functors, so let me write sigma I inverse. This is the functor corresponding to the complex of bimodules sigma I check. So the relations we see here is just sigma I inverse is isomorphic to, well, what endofunctor do you get if you take a complex of an modules and you just tensor with an as an an bimodule? The same thing. So this bimodule acts by the identity functor. So this relation just says that these guys are inverses. In particular, the sigma I are autoequivalences. And the other relations just tell you that they braid. So, etc. So we get a braid group action. So thus, the braid group acts on the homotopy category of left an modules by autoequivalences. And as I've defined it, since I haven't told you what these isomorphisms are, this is a weak action in the sense that we discussed last time. This is a weak action, but it can be made strict. But I won't say much about that. Okay, so any questions about the definition? To every element in the braid group, we now have a well-defined up to isomorphism endofunctor of this category. Okay. All right, so what can we say about the braid group using this action? So let me give you a couple of example computations. these are so I'm just going to spit out the answers. These are not difficult computations, but I think if you haven't done computations like this before, it's probably not obvious how you go about doing them. So anybody who's interested in working through a couple, I'm happy to go through it in detail. So let's look at P1. So this is the module, the left AN module consisting of paths which end at 1. So we can act by the braid sigma 2 on this module. And we're going to get a complex of modules. And what complex of modules are we going to get? I'll just write it down. It's a two-term complex, P1 mapping to shift of P2. And let me just write down a couple other examples. So what if we did this on the other hand? And this guy's in homological degree 0. Move this over. This is just to give you a sense notationally of what a complex of modules looks like. So you still have a P1 in degree 0, mapping to P2 minus 1. And now we're going to act by sigma 1 inverse, and we get another P1. And I'll explain why I drew this differential with vertically in a moment. How about sigma 1 inverse of P1? That's this is now in homological degree 1. So this is the piece in homological degree 0. This part here is in each of these complexes. Let me just box the part in homological degree 0. Okay. So this is kind of what you get. You see, you start with a module, tensor it with complexes of bimodules. You get some complexes of bimodules. They look however they look. So what we will explain on Friday is the fundamental observation of Kovanov-Seidel, which is there's a ton of topology hidden in these complexes. In particular, the way these complexes look captures the topology of curves in the punctured disk with the action of the mapping class. So in fact, each of these complexes each of these modules corresponds to a curve in the punctured disk. Ellie drew these curves. I'll draw them again on Friday. And these complexes over here also correspond to curves in the punctured disk. So there's a lot of topology behind the scenes here. So that's part of what we'll talk about on Friday. Okay, but what I want to say first, what I want to talk about in the last few minutes, is I want to address the following question. So now, there's lots of questions about the braid group that you can try to answer by looking at this particular action. So here's one. The question. So, okay, so let's say we have a braid. So we know there is an autoequivalence, which I'm abusively going to denote by the same letter beta from complexes of AN modules to itself. Can we tell, well, say how can we tell whether or not this braid is positive by studying this functor? Actually, this is probably not the first question you would ask. The first question you would ask is, how can we tell if this braid is the identity? So actually, the and I'll say more about this, if not this time, then next time. But the faithfulness of this action actually gives you a solution to the word problem in the braid group. This is something that, that Ellie pointed out to me a while ago, and I think it's really a beautiful fact. So one of the goals will be to, I mean, each of these 7 proofs of faithfulness, in a sense, give you a different way to solve the word problem in the braid group. And that solution is purely linear algebraic. The point here, and this, I'll put a problem on the exercise to make this clear. The question of whether or not this functor is the identity functor is a linear algebraic question. Answering it involves doing Gaussian elimination on a matrix with scalar entries. That's all it is. So it is a purely linear algebraic question involving doing Gaussian elimination on a matrix to say whether or not this functor is acting by the identity functor. So, okay. So I'll come back to that, but I think that would be the first question you would ask. But I want to address this one. So how can we tell whether or not a braid is positive? Well, so here's a so I'll give you a flavor of the answer. So remember, a complex of AN modules consists of chain groups, which are AN modules. So you've got chain groups in homological degree 0. In, let me call this -1, -2. Where each chain group Ci is, well, each chain group, let's call it Ck, is a direct sum of a bunch of our left modules Pi, maybe with some shifts. Maybe a bunch of them. So in each chain group, you just have an A module, and then we've got some differentials. That's, of course, I'm just telling you, reminding you what a complex looks like. So here's a definition. A complex C is non-negative if, well, we're working the homotopy category, so all the definitions about complexes should be up to homotopy. So if it is homotopic to a complex whose chain groups are of a kind of special form. So the chain group in degree K is isomorphic to a direct sum of modules. Well, these are grading shifts of modules. So unfortunately, in this definition, we cannot ignore the gradings. Gradings are essential. Where these gradings, so we're in homological degree K. So I want these gradings to be greater than or equal to, confusing my convention here. Unfortunately, with my convention, I mean less than or equal to K. Okay, so what does that mean? So let me give you, so let's go back to these examples for a second. Here are 3 different complexes. This complex is a non-negative complex. In homological degree 0, there's a grading shift of 0 on the chain group. In the next homological degree, there's just a grading shift of -1. So I would have equality here everywhere. This complex here is not non-negative. This term is fine. It's in homological degree 0, and there's no grading shifts. This term here is fine. It's in the next homological degree, and there's a next grading shift. But this term is a problem, right? This term is a problem because it's here in degree 1, but the shift is by 2. This guy's also not non-negative. Because in homological degree 0, we have nothing, but in homological degree 1, we've got to shift by 2. So, so this is non-negative. This is not non-negative, and this is not non-negative. So, so let me call it com greater than or equal to 0 inside the homotopy category. Be the full subcategory of non-negative complexes. Okay. So here's a theorem which I'll state in the attribute. So let's say we have a braid. So then the following are equivalent. So the first is that beta is a positive braid. That's equivalent to the statement that the functor corresponding to beta preserves the subcategory of non-negative complexes. So this is just a statement in the braid group, or your positive braid. This is a statement I'm abusively denoting beta here by the endofunctor. If this endofunctor preserves the subcategory of non-negative complexes, so takes any non-negative complex to a non-negative complex, that's equivalent to being a positive braid. And actually, that's equivalent to the statement that when you just act on the special modules pi, that it takes just these pi's to non-negative complexes. So this latter part, you should think, this is a finite linear algebra check. I mean, this statement in principle involves checking something on an infinite number of complexes. This is a finite linear algebra check, which you could get a computer to do. So this is a linear algebraic check of checking whether or not you're a positive braid. So this, this theorem is mine with the Queffelec. And it builds, so the proof, it builds on sort of work in other subjects. So let's say insight of Bezrukovnikov, working in modular representation theory of Lie algebras and in algebraic geometry in characteristic P. So Bezrukovnikov, all of this is kind of a very baby case of some of the categories and braid group actions that he considers. Bezrukovnikov is the one who noticed that there's a compatibility between things like positive braids and certain non-negative subcategories. He uses this kind of correspondence to prove some rather amazing theorems in modular representation theory. And then also some work in algebraic geometry of Chris Brov and Hugh Thomas. So Chris Brov and Hugh Thomas were studying the derived category of coherent sheaves on a resolution of a type ADE simple singularity. There are braid group actions there, and they proved things about positive braids in those braid group actions, which are kind of very, very similar. In some sense, part of this is just a translation of those things. Okay, I'm going to take one more minute to say the last thing. So this actually, this is actually the first, not historically first, but first in the context of this proof, first proof of faithfulness. So a corollary of this is that the action is faithful. The action of the braid group is faithful. So corollary. The categorical action of Bn is faithful. Well, and the proof goes as follows. let's say you have any braid you like in the braid group. So we can write the braid, this is a fact about the braid group, you can write the braid as a product alpha 1, alpha 2, where alpha 1 is a positive braid, but sorry, let's say alpha 2 is a positive braid, and alpha 1 is a negative braid, so alpha 1 inverse is also a positive braid. So any braid can be written as positive times negative. So if you want to show that an action of the braid group is faithful, it suffices to show that you can distinguish positive braids. So if B acts by 1 in an action of the braid group on something, then alpha 2 and alpha 1 inverse, both of which are in the positive braid monoid, they have to act the same way. So it suffices to show that you can distinguish positive braids. And so the final statement I'll give here is another piece of this story, which is another theorem of mine with Queffelec. So the following two things are equivalent. So let's say this is now, let beta be a positive braid. So the first is that beta can be written with a positive generator sigma I on the right, where beta prime is a smaller positive braid than beta. So beta prime also a positive braid, which has to be smaller than beta. If and only if, when you act by beta on the module pi, so you land in the strictly positive category. So I defined the non-negative category as complexes where the grading shift was greater than or equal to the homological degree. But you can define the positive category as the place where the grading shift is greater than the homological degree, or less than the homological degree, depending on the convention. So in other words, this is something which is sort of at level 0, and if beta moves it up, that's precisely telling you that beta has a sigma I on the left. So this gives an algorithm for writing down a word for a positive braid in terms of linear algebra of this action. So this shows that the action distinguishes positive braids from each other. Which proves two things. One, it proves the faithfulness of the action. Two, it proves this theorem of Deligne and Briscoe-Saito that the braid monoid, the positive monoid embeds into the group. Why? Because we've just given an algorithm for distinguishing positive braids, and that algorithm took place in a group, the group of autoequivalences of a category up to isomorphism. So, yeah, sorry, I'm way over time, so I'll stop here.
So can your action of the braid group be generalized to an action of any Artin group on some sort of more general category of, say, like complexes over different kinds of bimodules over different kinds of
yes.
Zigzag algebra?
Yes. Well, you can take a zigzag algebra for an arbitrary graph, and that will give you an action of the Artin group of corresponding simply laced type. If you want to do general Artin groups, then you have to work in the world of Zergel bimodules. But absolutely, I mean, the braid groups of ordinary, this example action generalizes. What's not known in general is whether or not the action is faithful. That is from my point of view, big open question in that subject, and that's something I've thought a lot about.